Hello and welcome to the screencast on modeling with polynomial functions. In the previous video we found a formula for the volume of a cylindrical can as a function of the radius, given the constraint of spending only $15 in materials. If you have not yet watched screencast 5.3.2, you should go do so now before continuing. In this video we will determine the domain of the volume function we previously found. While calculus is needed to rigorously find the dimensions that generate this maximum volume, the polynomial volume function we found will also enable us to find a good estimate of the maximum volume. So we had a cylindrical can. It was being constructed so the base and top of the can cost $3 per square foot, while the sides cost $2.50 per square foot, and we only want to spend $15 on materials for the can. How can we write the can's volume as a function of a single variable? So we did this in Screencast 5.3.2. We found a formula for the cost that involved the area of the sides, or the top and the bottom, times $3, and the area of the sides times $2.50. And since our constraint was only $15, we had our equation 15 equals 6 pi r squared plus 5 pi r h. We chose to solve that variable for h so that we could substitute that quantity into the volume function, and that way our volume was a function of one variable. So we're going to go on and we're going to find the domain of the volume function. So first of all, think in the context of this problem. The domain is the radius. And so if we wanted to estimate the domain, we could actually graph our volume function, and we know that the smallest radius that would make sense would be 0, and the greatest radius that would make sense. So we look at this volume function. The volume is increasing, and then as the radius gets bigger, the volume actually starts to decrease. That's because if we make the radius bigger, we're going to have to make the height smaller since we only have $15. So eventually when the radius gets to 0.892 feet, we end up with no cylinder again. The volume would be 0. So there's an estimate for our domain, but we can also find the exact value for the domain. And so I think it's probably obvious that the smallest radius, right, the minimum radius is 0. Right. If the radius is 0, we don't have a cylinder. The harder part is determining what is the maximum radius. And here it's important to remember again that because we only have $15, if we make the radius bigger, we're going to have to make the height smaller, right? So if I were to increase the radius of this cylinder, then I'm using up more material that costs $3 per square foot, which means I'm going to have less money to spend on the sides, so the height is going to have to get smaller. And so one thing you could think about is that as the height gets smaller and smaller and smaller, the radius can get bigger and bigger and bigger. So the maximum radius actually is going to be related to the minimum height, which would be a height of 0. So if we have a height of 0, that's going to give us no cylinder, but if we went just close to a height of 0, then the radius would be really, really big. So what I'm going to do is take this constraint equation that involved the radius and the height, and I'm going to let the height equal 0. Because I know if the height gets really close to 0, the radius can get bigger and bigger. 5 pi r times 0 is 0. So I just have 15 equals 6 pi r squared. Divide both sides by 6 pi. Take the square root, so we'd have technically plus or minus the square root of 15 over 6 pi. But this is a problem involving the radius. We cannot have a negative radius, so r would equal only the positive square root of 15 over 6 pi. That would be measured in feet. So that is actually the maximum radius. So the exact value for our domain would be a radius of 0 all the way up to the square root of 15 divided by 6 pi. So again, we did that by thinking about the other variable getting really, really small and then using our constraint to see what r would equal when that other variable h was really, really small. All right, so the other thing we can do with these constraint problems is actually figure out how to maximize the volume, for example. In calculus, you'll have a much more thorough way of doing this, but here we can use the graph of the volume function to help. If we want to find the dimensions of the can with the maximum volume, we're going to look at this maximum point on the graph. We know the inputs are the radius and the output represents the volume. So we already know the second question, what is the maximum volume of the can? All right, the maximum volume is going to be 1.0301 cubic feet. And then the dimensions, well, we can see from the graph that the radius, when the volume is 1.0301, the radius r is approximately 0.515 feet. And we would also need to find the height. So again, we're going to go to the constraint equation because that's the only equation we have that relates the radius and the height. And we would take 15 equals 6 pi r squared plus 5 pi rh. Substitute the 0.515 in for r. And I will let you simplify that and do the algebra there to get h alone, but you would find out that the height is approximately 1.236 feet. So the dimensions of this can would be a radius of approximately 0.515 feet, a height of approximately 1.236 feet, and that would produce a maximum volume of approximately 1.0301 cubic feet.